Hi students, and welcome back to our second and final lecture video for this week about conjugated compounds. In the last lecture, we talked about we talked about benzene and substituted benzenes and their nomenclature. We also talked about what constitutes a aromatic ring and why that produces bonds of exceptional stability relative to other alkene bonds. We then discussed the ways in which we might determine whether a molecule is an aromatic or not, using two conditions. One, it must have conjugated pi bonds, it must have conjugation all the way around the ring, and it must obey Huckel's rule, stating that it has a 4n plus 2, where n is the 0, 1, 2, 3, so forth, number of delocalized pi electrons. And then we finally finished off by stating that we should watch out for molecules like pyridine, where the electron pair is delocalized and in an unhybridized p orbital, relative to a molecule like pyrrole, where the lone pair here is in the unhybridized p orbital and thus is available and to move around the ring and be delocalized. We're now going to talk about polycyclic compounds that may also be aromatic. These include compounds like so-called naphthalene here. You can see that the double bonds are conjugated, double single, double single, double single, all the way around. Anthracene here, also double single, all the way around, every direction. And phenanthracene here, also conjugated, double single, double single. In terms of aromaticity, we can see the stabilization energy based on the energy required to fully hydrogenate the ring like we did before. So when we look at benzene, for example, the average stabilization energy per ring is 152 kilojoules per mole. And for this is the total stabilization energy. Here's the stabilization energy per ring. And we can see that although it's not as high as benzene, it's still pretty high on the order of benzene. And so that gives us evidence that these are indeed also, these polycyclic aromatic hydrocarbons are also particularly stable and aromatic. This is an issue because these benzene and these other polycyclic aromatic hydrocarbons, or PAHs as they're called in environmental chemistry, these are products of combustion of incomplete combustion of fossil fuels, and they're highly carcinogenic, and they're in our air as a result, especially in Southern California, as a result of combustion in automobile engines. Fortunately, our regulations in California, particularly because of LA air, are stricter than anywhere else in the nation, and we have, for the most part, reduced the concentrations of these kinds of compounds in our air significantly since the 80s, the 70s, and the 80s. So now we're going to begin to talk about reactions of aromatic molecules. And the reactions of aromatic molecules, as we have seen, are significantly different from those that are not aromatic. We've seen, for example, that you cannot very easily and very simply do addition reactions to an aromatic ring like you would to a normal alkene. These reactions must be much more forceful. The exceptional stability of the aromatic ring means that any reaction that would break this aromaticity would cost a lot of energy and will be less favorable than it would for a non-aromatic hydrocarbon or organic molecule. So a carbon that's directly attached to a benzene ring, this terminology that we have, it's called the benzyl position. So being directly attached to the benzene ring is called benzyl. Being one carbon away is called aryl. One carbon away here, benzyl position, rather being right on the ring is called aryl. Sorry about that. So aromatic rings and alkyl groups are not easily oxidized. Alkanes are spectacularly unreactive. Benzene rings also spectacularly unreactive. It's hard to make them react. So if you try to expose them to an oxidizing agent, you will not oxidize them. So for example, our classic oxidizing agents were sodium dichromate with sulfuric acid or producing chromic acid, or we also had PCC in the presence of CH2Cl2, dichloromethane. That was another common oxidizing agent we used in chapter 12 for alcohols. At benzylic positions, though, not on the ring, but at the benzylic position, these can be oxidized quite readily. And the reason is because you end up with situations that also contribute to that aromaticity instead of breaking it. So if we have a substituent here, an alkyl substituent on this benzene ring, and we expose to our classic oxidizing agent, chromic acid or sodium chromate and sulfuric acid and water, we will actually get the oxidized product, fully oxidized, of a carboxylic acid. That said, the benzyl position must be open. If we have a completely substituted carbon atom with no hydrogens attached, we cannot oxidize it. It has to have at least one proton attached to undergo the oxidation. We can also use potassium permanganate. That's the other oxidizing agent we learned about in the alcohol chapter. That will do a similar thing, except the carboxylic acid here will ultimately be deprotonated in water because it's more acidic than hydronium. However, more acidic than water. But if we introduce a lot of hydronium, we can and bring the pH down low enough, we can protonate this deprotonated carboxylic acid and get the in this case the carboxylic acid group here, or benzoic acid altogether, this is called. Obviously, there's some carbons lost in this process. These have not been mentioned, but this is a byproduct that we do not concern ourselves with. Benzylic positions are similar to allylic positions, so we can also do other reactions with them. And again, this is because this would be going through a radical intermediate, right? So if we expose this to NBS to do allylic bromination, as we saw in chapter 10, we can brominate at the allylic position. And you can consider why, right? A part of this, if you consider the mechanism of this, it makes a lot of sense why this would occur. The initiation, the NBS provides for us a bromine atom, which can initiate this radical reaction by being involved in initially a proton abstraction here like this, and that leaves a radical here on this carbon atom. And so now if we redraw this right here, we can see that this is a benzylic radical, which provides exceptional stability due to the fact that it can undergo a lot of resonance, right? So the resonance would look like this, and we'd have one arrow here, and then that would produce for us this structure right here. We'd have the radical here, and we'd have there'd be no double, the double bond would no longer be there right here, but we would have now a double bond right here. And then this would continue. You'd have subsequent resonance arrows as well, all the way around. So that's your radical resonance there. Hopefully you remember the radical resonance arrows as well from chapter 10. And this contributes to the stability of the intermediate, which allows for this reaction to happen. And that's why the benzylic position, if you have a carbocation here, if it goes through a carbocation intermediate, it goes through a carbanion intermediate, it goes through a radical intermediate. These are all going to be resonance stabilized by the benzene ring. And so these reactions will happen quite readily. So we can do a free radical bromination using NBS, N-bromosuccinicide, as it's called, to brominate at the benzylic position. We can also do substitution reactions. Recall that an SN1 reaction is going to go through a carbocation intermediate, right? So if we expose this to water, for example, and this is going through a carbocation intermediate, the first step in an SN1 reaction would be the loss of the leaving group here, which would produce for us this intermediate. which is carbocation, and this would be an allylic or benzylic rather carbocation, and again we'd have exceptional stability of this intermediate due to the resonance here, and so the resonance arrows would look like this. Oh, Dr. L, I thought resonance was way back in chapter 2 and I could forget about that. No, you can't. So this would produce this resonance structure right here, where we would now have double bond here, and these would still be here, but we'd have the carbocation right here. And this would go all the way around the ring. And so due to the fact that there's exceptional stability to this carbocation intermediate, SN1 reactions will occur quite readily. This would be followed up by a nucleophilic attack by the water and a subsequent deprotonation. So if you're wondering why we spent so long reviewing 212, and we're trying to know these mechanisms, because it really helps you understand why these more recent reactions that we're learning work, so that you don't have to memorize that this happens, right? You don't want to memorize benzylic bromides readily undergo SN1 substitution, because if you try to memorize that, you're soon going to forget it. But if you think about why that might be true, because you understand that SN1 mechanism begins with the loss of a leaving group and the formation of a carbocation intermediate, then you would understand that because benzyl carbocation intermediates have exceptional stability due to resonance, that can allow for this reaction to occur. In this case, we had a tertiary alkyl halide, which is why the SN1 reaction was favored. We also had a weak nucleophile, weak base, which also encourages SN1 or E. Right, we'd also have an E1 component to this as well, which wasn't mentioned, but we would have some E1 occurring as well. If we have a primary alkyl halide, the SN2 reaction would dominate. And so here we would have a at the benzylic position, we'd have a simultaneous nucleophilic attack of the hydroxide on the carbon and simultaneous leaving of the bromide leaving group, SN2 fashion. Benzylic bromides also undergo E1 and E2 elimination. So if we have a strong nucleophile, strong base, and we have this tertiary carbocation, tertiary alkyl halide, remember that this is going to really slow down the SN2 reaction. So the E2 reaction will be what will dominate. And in this case, notice that there's only one possibility for the elimination. You cannot eliminate here. So you end up eliminating right over here. These two positions are equal. And so if we wanted to look at the mechanism, again, very important to understand the way the mechanism works, so you don't have to just randomly memorize these things. The way the mechanism is going is that we're having a simultaneous proton transfer and simultaneously loss of the leaving group, ultimately leading to the pi bond. So that's the mechanism for that one. Super important that you understand that mechanism. In the case of concentrated H2SO4, we can do an acid catalyzed dehydration. And in the acid catalyzed dehydration, that would begin with, since this would occur via E1, because we have a weak, here we're having a bad leaving group, basically. We're having a weak, the base here would be water, in fact. This is an aqueous solution. So we have a weak nucleophile, weak base, tertiary position. This will result in SN1 and E1 reactions. The SN1 would just produce another alcohol in the case of water, so we're concerned only with the E1 reaction in this case. This would begin by the loss of the leaving group, producing a benzyl carbocation intermediate right here, and then we'd have a subsequent nucleophilic attack by water, and then that would be followed by, that would go nucleophilic attack right there. Whoops, sorry, not nucleophilic attack, I was thinking substitute. Sorry, we'd have a subsequent, that would just bring us back to our alcohol. That would happen, but it would just give us back our alcohol, right? So here what would be removed, we'd have a proton transfer here, which would ultimately be the removal of this proton and then the formation of the pi bond. So again, understanding those basic, if these mechanisms are feeling foreign to you, you need to go back into chapter 7 and really understand chapter 7. That is foundational for all kinds of different reactions that we continue to talk about throughout this semester. So overall, here's a summary of the reactions that we've talked about now, the benzyl reactions. If we have a primary benzyl position, this can undergo radical bromination. Then we'd have a primary alkyl halide, which could then undergo either SN1 or SN2 reactions. SN2 probably favored due to the lack of steric hindrance here, unless we had a weak nucleophile, weak base. Even then, SN1 would really be mostly SN2 occurring here. If we can also oxidize at the benzyl position, we can use sodium dichromate with sulfuric acid and water, or we can use potassium permanganate with sodium hydroxide. We can also oxidize this tertiary benzyl position as well, and as long as there's one proton there, which there's one hydrogen here, as long as there's one hydrogen attached, we can do the oxidation and get the carboxylic acid here. We could also do radical bromination on this one as well. Remember, radical bromination will involve use of NBS. And then once we've got the tertiary alkyl halide, we can have it undergo an SN1 reaction with an alcohol or water. We can have it undergo an E1 or E2 reaction with the presence of a strong base. And if we have a substituted at the benzyl position, we can do an elimination, so we can do an acid catalyzed dehydration, for example. Since this is a tertiary position, H2O4, water. Here, concentrated H2SO4, do an E1 reaction. So this is a summary of all of the reactions that we have just covered in the benzyl position. And then these alcohols can go on and do other alcohol reactions. If you're doing a synthesis, for example, and this alkene can go on undergo alkene reactions, like we discussed in chapter 8. Now, we did say that these benzene has exceptional stability, and the pi bonds here themselves will be spectacularly unreactive. However, if we hydrogenate at very high pressures with lots of hydrogen and very high temperatures, we can force hydrogen to be added across these double bonds. And so we can, currently each of these would have one hydrogen attached, right? But we would essentially add one hydrogen to each one, and after they're done, we'd have two hydrogens attached. And this would be true in each of these. And this would be exothermic, as we discussed previously, but it has a very high activation energy. So if you're looking at an energy diagram, it would be like, yeah, it's exothermic, but the activation energy is super high. So activation energy. And this would be delta G, is going to be super high. So that's why we use such forceful conditions, high temperatures, high pressures, to really force this from the reactants to the products. Now, when it comes to hydrogenating at the benzyl position, this is super easy. Notice the lower temperature, lower pressure here. Hydrogenating in the benzyl position is much, much easier for the same reasons that other reactions at the benzyl position are easier. You can see that it's not as favorable thermodynamically because you're basically not losing these super strong bonds and getting these lots of additional strong bonds. You're only just getting two bonds to hydrogen. Note that there was two hydrogens here, but now there'll be two hydrogens after the hydrogenation on, actually there were two here. There will be three on this one now. We added this hydrogen and this hydrogen. We're only hydrogenating one double bond, so we only get less energy, but this happens much more readily. You don't need to have these very forceful conditions to hydrogenate the benzyl alkene. Now, in terms of reducing the benzene ring, we can reduce the benzene ring. Remember, a simple definition for reduction would be losing oxygen atoms or bonds. This doesn't always work, but it usually works. Very much simpler way. Or gaining hydrogen atoms or bonds. So here we can do a reduction. This reduction is analogous to the dissolved metal reduction in alkynes. It makes the use of sodium. The mechanism is very similar to the dissolved metal reduction. So we have sodium in methanol with a ammonia solvent. The ammonia solvent is there because, remember, the pKa of ammonia is like 38. So this ensures that we are not likely to protonate our intermediates here, which will be ionic and radical intermediates. Remember this mechanism, if you remember from chapter 10, the dissolved metal reduction for alkynes proceeded through a kind of ionic and radical mechanism, kind of unique mechanism. So recall in that mechanism what occurred was that we had the sodium with a single electron, and so we had this kind of radical mechanism going on where the sodium gave an electron, and I drew this arrow wrong. I'm going to undo that. Oops. Oh. Erase that real quick. I have a button for erasing. Oh, no. There we go. And so we have one electron that goes to this carbon atom right here. One of these electrons going to go to this carbon atom, and then we're going to have a radical on the carbon here. So we're going to have a carbanion here afterwards and a radical. And that's going to be the first step of the mechanism. So that's shown right here. And in fact, I did botch that a little bit. There's also this one here, which can also produce a pi bond. So but that was what I'm saying is it's somewhat similar to the alkyne dissolved metal reduction, right? And so here's the actual arrows. So let's look a little bit more closely. The other one had a little bit of an error in that because we're aromatic here, we're all the way around, we have an additional step that's a little bit different from the dissolved metal reduction. In fact, so the same first step, we have one electron here going onto the carbon involved in the pi bond, and we have one electron going here to the carbon involved in the pi bond. The difference here is instead of this electron going right here on the hydrogen, remember all these electrons are delocalized, so it's going to instead go into the formation of a pi bond right here. And then we're going to have this electron from this pi bond contribute to the pi bond here. And then on the opposite side of the ring where we have the carbanion, we're going to end up with the radical electron. And so here now we have two electrons on this carbon. It has 3 bonds and 1 lone pair, so it's a carbanion. So that's going to be extremely basic. The reason why we have the methanol in here is to protonate that one. But we don't want to protonate it with the ammonia, so that's why the ammonias are solvent. So after that, it's followed up by a proton transfer here. So we end up with this carbanion here going and grabbing this proton, and then that will leave behind its electrons. And so now we have this protonated radical here. We just have this radical. Now remember from the dissolved sodium reduction, the next step in the dissolved sodium reduction is that we have another sodium atom that provides its electron, right? And that's going to be the same next step here. We're going to have that sodium atom provide its 1 valence electron. That's going to go ahead and provide that electron, now making 2 electrons here. So we have a lone pair on a carbon with 3 bonds. That's a carbanion. And again, we're going to have the methanol provide the proton to protonate that. And now our reduction has been completed. And we have the pi bonds now are on opposite sides of the ring. So this is referred to as the Birch reduction, and it has a lot of similarities to the dissolved metal reduction from chapter 10. I remember these mechanisms kind of as a chunk, right? And the fact that they're very unique, being both ionic and radical at the same time, which is it's the only reaction we've seen that's like that. Note that the Birch reduction doesn't completely reduce the benzene ring, right? These could be further reduced. So it's a soft reduction. At this point, though, we would no longer have a aromatic ring. So we could go on, if we wanted to further reduce these, we could. Although we could have just reduced them directly. But these would be much easier to reduce now, these double bonds. We could simply, have a low temperature hydrogen, low pressure, low temperature H2 platinum would do the job if we wanted to further reduce this. Notice that these carbons here are now sp3 hybridized, while these ones here are sp2 hybridized. We've converted, before they were all sp2 hybridized carbons on the benzene ring, and now 2 of them are sp3 hybridized and 4 of them are sp2 hybridized. Now, we've seen here in previous reactions that we could have the presence of other groups here. Now, if we have a carbon, now the R here represents carbon and some other stuff, right? So there's carbon and it might have other things attached or whatever. If we have a R group here, a carbon atom, this is equal in electronegativity to the carbon. We consider this electron donating. It can give electrons, the carbon atom. If we have an electron donating group, that's going to mess up this reaction here. It's not going to occur in the same way, and we will not observe the Birch reduction. It's because the electron donating group destabilizes the radical cation, and so the reduction does not occur. Remember, this occurs through a radical right here, and having a carbon atom is going to destabilize that radical. And so it's not going to work if we have a carbon atom attached. However, if we have an electron withdrawing group attached, anything with high electronegativity or any carbonyl like this ketone here, this will actually support this reaction. And so the reduction will occur. And it will occur in the same way as we saw for the benzene ring. And so an electron withdrawing group will support this reaction and cause it to go more readily. An electron donating group, essentially carbon, or it could be anything with low electronegativity, would not support this reaction because it would destabilize the carbocation inner. When it comes to spectroscopy, so in chapter 15 we discussed the NMR spectroscopy of benzene rings. In chapter 14 we discussed the IR spectroscopy of benzene rings. This is just a reminder that when we have a benzene ring, we're going to get, in the IR spectrum, we're going to have sp2 carbon CH stretching, which will lie just above 3000. We're going to have aromatic overtones that occur anywhere from 1700 to 2000, and those aromatic overtones often look like a lot of small peaks that occur in the 1700 to 2000 region. We're going to have a CC double bond stretch that occurs around 15 to 1600. And we're going to have bending and stretching frequencies that are going to be in these are going to be in the fingerprint region. So you're probably not going to spot these as easily, these ones that are occurring in the fingerprint region, right? Whoops, or fingerprint. So these ones you wouldn't be expected to label or anything. These other ones you should be able to spot in an IR spectrum. And so you can see here we have the sp2ch stretch. Remember, when we analyze the IRs, we draw a line here at the 3000 mark, and to the right here we'd have sp2ch stretches, or to the left rather, a little more to the left of that we would have spch stretches. We have these aromatic overtones here occurring in the 1700-ish region to 1800-ish. And then we have the CC stretches, which occur somewhere around 15 to 1600. CC double bond stretches. When it comes to NMR, for NMR, we're going to observe chemical shifts for the aryl hydrogens that are going to be 6.5 to 8 ppm. And then we'll have some downshifting of the benzyl. The hydrogens on the benzyl carbon will be shifted to maybe 2 or 3. And then if we go 1 carbon away from that, we get a little bit of shifting here and higher chemical shift, but not by that much. Recall that in terms of the splitting of the protons, the H1 NMR is useful for multiple substituents here. So if we have a benzene ring here that that we have the same group on either side here, we're going to have a plane of symmetry here. All 4 of these hydrogens will be equivalent, so they'll give one one signal in the chemical shift around 6.58 ppm. If we have 2 separate hydrogens here, we're going to end up with 2 doublets occurring. And sometimes these doublets, if these 2 are similar in electronegativity, these doublets will be right on top of each other. In the carbon-13 NMR here, depending on the position of substituents, we can have multiple signals. In this case, with this symmetry here, these 2 carbons would be equivalent. So this one would be equivalent to this one, so this would also be 1 right here. And so we get 1 signal for 2 hydrogens here, and then these would all be 2 here. And so we get another signal representing 4 carbons. If we have substituents in the ortho position, we'll have 3 different carbons, the ones attached to the groups themselves, and these 2 would be 2 others, and then this would be the third, and each would give you a signal representing 2 carbons. Of course, when it comes to carbon NMR, you can't really trust the integration, right? We don't really rely on that. If we have 2 separate groups, every carbon will be different here. If they're ortho, if they're meta, again, every carbon will have a different chemical environment. However, if they're para, we'll have one carbon attached to one substituent, 1 to the other, and then these 2 carbons, 2 and 2 here, would be the same, and these 3 carbons would be the same here. And that would give us 4 separate signals. Likewise, if we have 2 groups here in the meta position, we'd have this carbon is different from this one. However, these 2 carbons would be the same, 2 and 2 here. Likewise, here with only 1 substituent, we'd have 2 carbons, the one attached to the substituent, the one opposite, and then 3, 3. Finally, graphite. Graphite is what's in your pencil lead. Graphite is also a highly conjugated structure with fused aromatic rings. It ends up flat like this, and what happens when you're drawing with your pencil is that these flat layers are layer by layer scraping off, and that's what gives that kind of smooth scraping to the pencil and puts that thin layer of graphite on the sheet. In addition, graphite is used to lubricate locks. They'll put the locksmith will put that in there because these sheets of aromatic rings slide along one another. So the structure itself is extremely strong on each sheet, but the sheets are not strongly bound to one another, so they slide across one another in a way that gives graphite very special properties and can be used as lubricants in solid locks like that, and also as pencil lead. Finally, the structure of Buckyball here, which is composed of 60 carbons, which are all aromatic rings, forms a very stable ball structure here, and things can be trapped within this structure to deliver them, and this can be used synthetically or in other ways. And so finally, carbon nanotubes are so-called fullerenes. They're made into tubes. So these are aromatic rings here that are arranged in a tubular-like structure. So instead of being a ball here, they're arranged, or a flat sheet like this, they're arranged in this tubular structure. And these have many applications because of their aromaticity. The electrons are completely delocalized, so these can be turned into kind of wires that can conduct electricity. Also, they can be used to make many conductive different types of materials here. And so, unfortunately, partial nanotubes, polyaromatic hydrocarbons, are carcinogenic. So the actual structure of these is very important, and that's been the engineering trouble in making nanotube applications, is that you have to be, in terms of the synthesis, these have to be synthesized as full tubes here and can't have little polyaromatic hydrocarbons attached and falling off, essentially. Otherwise, those could be carcinogenic, particularly when used in applications like biomedical ones. And so that has been one of the challenges in terms of bringing these theoretical structures into practical applications. And so that's going to be the end of our lectures this week for aromatic compounds. Good luck on your studying today, and I would also encourage you, if you've had a recent exam, to go over that as well if you have a little extra time this week, since this is a little bit of a shorter chapter. But I hope you have an excellent week, and I'll talk to you all soon. Have a good one.